everyone, welcome to the lecture number 19 of this NPTEL lecture series on charging infrastructure. In previous lecture we have discussed about totem pole PFC. We will continue our discussion in this lecture as well. So let us see what we have understood as of now. We understood that this totem pole PFC is nothing but a derivative of bridgeless PFC, where we do not have any diode bridge rectifier at the first stage. And we have also understood that in this S1 and S2 switch are the one who are switching at very fast switching frequency FSW, which is far more greater than line frequency Fs, and while the diodes are actually being, it is on for the one half cycle, while other half cycle it will be off. So diode switching with the line frequency, while the switches are switching at a high switching frequency. So this we can easily take it in a form like we can also use a switches as well, having a free wheeling diode or the body diode if we use MOSFET. So we can also realize this converter having 4 switches, and all the 4 switches S1 and S2 are switching with a high switching frequency FSW, which is very much higher than the line frequency, while the S3 and S4 are switched only once in a line cycle. So they are switching at a very slow switching frequency, which is Fs, same as the line frequency. And in one line cycle we have several or so many switching cycles depending upon how much times the FSW as compared to Fs. Similarly, we have also seen the RMS current of S1 switches, which is shown over here. Here we have this, we can easily put Is is nothing but Is peak sin omega t. We assume that this converter is drawing unity power factor current from the source. And we can also know that we also have this inductor and capacitor. So this inductor and capacitance value is same as that of boost PFC converter, where PL indicates the load power, Fs is nothing but the line frequency component, and delta V naught is the allowable voltage ripple on the capacitor, V naught is the output voltage, while L is nothing but V naught divided by 4 delta IL or delta IL max, which is the maximum allowable current ripple times FSW. And if we look very carefully, this capacitor, since it is the having a single phase power factor correction converter, having the unity power factor current drawn from this input source, so this capacitor will have second line harmonic component on its voltage. So it has, so output voltage has the second line frequency component of voltage riding over the DC value V naught. Now let us see, as in the case of boost PFC, where our control objective was to have the output voltage getting regulated, at the same time making sure the average current which is being drawn from the source is nothing but having the unity power factor. So both the things has to be ensured while doing the closed loop control. So let us try to see how the closed loop control look like. Again, in the closed loop control, it is we are trying to do the closed loop control of average current flowing through the inductor, and here the average current flowing through the inductor is nothing but same as that of the current which is been drawing from the source. So if we can ensure that the average current flowing through the inductor is having the sinusoidal variation and having the phase angle same as that of the AC voltage, so we can ensure that the IS current or the grid current which is being taken is also having the unity power factor variation. So here what we do is, again our main requirement, we will define the reference voltage, whatever reference voltage we want, we will do the summation of that, send it to the voltage controller. This voltage controller will be, output of this voltage controller will be clamped to the maximum allowable current in the converter, because before doing the closed loop control we would have already selected the devices having the required currents. So we have already defined that rating, so that is why the clampings are needed, and that will be sent to a multiplier block. player block. Now if you recall, in case of boost PFC we have multiplied the output with modulus of unit sine omega t, but here we will multiply it with the unit sine which is just a unit sine omega t. Generation of this unit sine omega t is critical in order to ensure that the current drawn from the source is having the same frequency component as that of line frequency and also having unity power factor operation. It is because our grid voltage have small variations in frequency around the nominal value, that means 50 hertz or 60 hertz, and also have harmonics in it. So we need to track these small variations in frequency to accurately detect the zero crossings and matching the sine omega t, which is difficult things to do. There are a lot of literature available addressing this problem using advanced phase lock loops and filters. However, in this particular lecture series we are not discussing that. Here we can assume that we can just sense this voltage, grid voltage, and we can just we can just divide it by the peak value of the voltage which we are obtaining, and that we can directly multiply it with the current reference which we are the magnitude which we are getting at the output of the voltage loop, and this is nothing but will define the is reference, you can say, the current which we are getting over here, because our IL is nothing but IS, and again it will be compared with the this comparison we will take down from the circuit. So it is nothing but the IS, so we can take from here, and that is then send it to current controller. Again output of current controller is sent to gain Ki block, and that will be sent to the modulator block, does nothing but calculate the duty ratio, the whatever duty ratio is coming, and then depending upon the grid voltage, whether it is in the positive half cycle or negative half cycle, decide the switching of these switches, like whether it should be D or whether it should be 1 minus D. Accordingly these two switches will be defined, while if Vs is greater than 0, your that means positive half cycle S4 is on, if it is in negative half cycle S3 will be equal to 1. So here you will get the PWM for PWM of S1, PWM of S2, PWM of S3, and PWM of S4 you will get. And this output voltage what you are having, this you can sense and you can feed it back to the reference voltage. Similarly, whatever current feedback we are seeing, we can take sense it and using the current sensor and send it back to the loop. So here we have IS feedback, here we have V naught feedback. And again, as we have derived those closed form solutions, or we have defined the GIS of S or GV of S, here also the same way we will also obtain the same GIS of S and GV of S, and then we can we can design our controllers following the steps what we have seen in case of boost PFC case. And using this method we could be in a position to basically ensure that whatever we are having the unity power factor current drawn from the source, at the same time we are maintaining the voltage at a reference value. Now if we talk about modulator block, so the input of the modulator block is nothing but D, duty ratio D, which is varying with T. So that we can again PWM S1 can be generated in similarly. Here in the modulator block we also need to sense, we can also sense this voltage, and we can send it to this modulator block. Similarly we can actually send it to this unit sine omega t block generation, and we can use the same thing to generate the unit sine waveform or sine omega t. Now here if we look very carefully, this why we are taking this, just to ensure it is in positive half cycle or negative half cycle. So our modulator block will have the duty ratio which is compared with the carrier. This duty ratio d of t, what we are getting from d of t, depending upon the Vs of t, we will generate ds1 of t, ds2 of t. Okay, using, you can either use lookup table or you can just do the relation operation you can do and find out, because we know ds1 of t is nothing but equal to 1 minus d of t in whenever we have Vs greater than 0, and whenever Vs is less than 0, ds1 of t is nothing but equal to d of t. So we can write down this ds1 of t is nothing but equal to 1 minus dt when Vs is greater than 0, and it is d of t when Vs is less than 0. Similarly, ds2 of t is nothing but 1 minus d of t when Vs is less than 0, and d of t when Vs is greater than 0. So for that purpose we can use this particular block, and for generating the PWM for S3 and S4 you can take again the relation operation. You can take Vs and then generate ds3 of t and ds4 of t. How this will look like? ds3 of t is equals to 0 for Vs greater than 0 is equals to 1 for Vs less than 0, and ds4 of t is nothing but equal to 1 when Vs is greater than 0 and 0 when Vs is less than 0. So using these two things you can generate that, and these things you can take this duty ratios. Let's say you have taken ds1 of t through a comparator block and having the carrier. This is nothing but your carrier. Now this carrier will be at a higher frequency, nothing but the carrier frequency is nothing but FSW, same as the switching frequency of S1 and S2, and that will give you PWM of S1. You can also take ds2 of t, or you can generate from here itself not and generate PWM S2. Similarly, you can take the same way comparator block ds2 of t, and this you can compare, and so not ds2 of t, you can take ds2 of t, that's not a problem. This you can remove, you can just write ds2 of t PWM of S2. Similarly, you can take ds3 of t, compare it with carrier, send it to PWM of S3, and send it to compare it with the carrier to obtain PWM of S4. Accordingly, you can design your modulator block. This is nothing but the things which are there in the modulator block, and that's when your all the PWMs are generated, and you can send these to the gate drivers of the switches. And if you take fundamentally this converter and the boost PFC converters are the same from the operation perspective, that's when all the GIS of S and GV of S remain same, and accordingly we can also select our voltage controller and current controller. Now if we look very carefully, we have only discussed about the advantages of this converter. Now this converter also have several disadvantages. I mean, the disadvantages are, let us discuss those disadvantages. If you look very carefully, this particular converter, in this particular converter we have the fast switching leg which is S1 and S2, and we have a slow switching leg which is switches once in a line cycle which is S3 and S4 switch, having S3 and S4 switches. So now if you look very carefully, this particular system has this switch S1 and S2 which whose duty ratios are varying continuously in one line cycle which goes from here to here. If we try to draw the line cycle, it is nothing but from here to here, T, which is nothing but 1 by Fs. In this entire line cycle, if we look very carefully, during the crossings, during the zero crossings, whether the the line voltage is going from positive to negative or negative to positive, what we will see is that during the crossings our duty ratios of the devices S1 and S2 are changes abruptly from 0 to 1 or 1 to 0. If we see when it is going from positive half cycle to negative half cycle, that means the voltage, the grid voltage is going from positive side to the negative side. We see that our the duty ratio of S1 changes from 0 to 1, while the duty ratio of S2 changes from 1 to 0. Similarly, in case when it is going from negative to positive, that means when the voltage is going from negative side to positive side, the duty ratio of S1 changes from 1 to 0 and S2 changes from 0 to 1 abruptly. Now, and if we see very carefully our duty ratios, let us say if we are using just the S3 and S4 switches. So, if we try to draw our duty ratios of, let us see if we draw the duty ratio of our DS3. So, DS3 is on always during the negative half cycle. So, we can write it is 0 in positive half cycle and it is directly going to 1, then again to 0. Okay, here it is 0 going up to here. Similarly, if we see the duty ratio of S4, it is 1 going to 0 and it is 0 for the entire T by 2 period. Again it comes back to 1 and goes to be there 1. If you look very carefully during the transition, there is also transition of S3 and S4. Whenever it is going from positive to negative or negative to positive, the duty ratios of S1 and S2 are changing from 0 to 1 or 1 to 0. At the same time, my duty ratio of S3 and S4 is also changing from either 0 to 1 or 1 to 0. Now, the synchronization of turning on to off or off to on of these four switches during zero crossings are the important concern, because in real world no two switches are symmetrical in nature, and you can never ensure that these timings whatever is there are synchronized. And also if we look very carefully, the RMS current of switches in these two legs may be different. That's when you also have to select different devices as well. So when you are selecting a different devices, it comes with different parasitic capacitances around them, and that's when they will actually have different turn on and turn off times. I mean the transition times during turn on and turn off are different, and that is actually lead to the spike in the inductor currents. Now let us see how that spike takes place. Now let us take first scenario. Now this scenario I am talking about the point where my voltage or the grid voltage is going from the negative to positive. That means I am talking about point A, this point A. So let me write scenario 1 at point A. Now this point is nothing but, let me write slightly up so that we will have space to write down our thing. So this is nothing but scenario 1, and if we try to see our point A where our Vs is going from negative to positive, that means near to the 0 crossing. And if we try to draw our currents, how our current look like? Our current, so if I draw the switching cycle average current variation, it will be looking like this. It is the same as that here, which is nothing but I can define this as Is average, while my actual current will be of the form having the ripple over this, as we have already know from our discussion. Again I am drawing in a very this fashion, or it is having a very the ripple, this ripple duration is very small. I have already exaggerated it just for your understanding. So this is my Is actual current, which will look like this, which will have the your line frequency component and a ripple component over riding over that. So if we look very carefully, our scenario 1 where we are going from negative cycle to positive cycle, during that time what is happening is, if we look very carefully, during that time my duty ratio of S2 is going from 0 to 1. So the DS2 goes from 0 to 1 and my DS1 goes from 1 to 0. That means I have kept my entire S2 switch on while my S1 switch is completely off. So that means S2 is on completely and S1 is off completely. Okay, during that instance when you are at this point, when you are at that point, my S2 goes to 1 and my S1 change just be after that point, after this point my S1 goes from 1 to 0. So that is what we are getting. Now at that time if you look very carefully, the status of S3 and S4, now the status of S3 and S4 should be my S3 should turn off and my S4 should turn on. Now if there is a delay, if there is a delay in turning on S4 switch, so what will happen? During that time my S3 is on, because you will be giving a dead time, and during the dead time, because you cannot turn on both the switches simultaneously, so what you will do, your S3 goes from on to off. So on to off it is going, that means you will just remove the gate pulses. So when you remove the gate pulses here, S4 was already off. If you look, S4 was already off. So S4 was already off. So when you remove the gate pulses, so what has happened, these diodes which are there, they are they will, depending upon the current in the circuit, they will change its status from I mean the diode of S3 or diode of S4 is on, and then only you are turning on the S4 switch. So there is some time zone where your S3 is, I mean the turning on of S4 gets delayed. Now during that time what is happening in the circuit is, you will see the voltage across this inductor. Let us see that now, since the gate pulse of S3 is removed, it is a dead time period, but due to current the body diode of S3 is on, and in that time S4 is already off. As a result, the entire V0 appear across switch S4 and the output capacitance of S4 is charged to this V0 voltage. And then in this circuit, and then in this particular circuit loop, if we see where S2 is on and output capacitance of S4 is charged to V0, the Vs value is nearly 0. So what you will get is the VL is equals to V naught. Whatever the voltage which is there on the output capacitance of S4 switch is actually coming across the inductor L. So we can write appearing across S4 switch. Now during this time what you will see is that since there is a positive voltage applied across the inductor, there is a positive, sudden positive spike current, because this voltage value will be very high. Generally if it is 400 volt, so this entire 400, assume this is the 400 volt, so entire 400 volt will come over here, and then you will see a sudden high slope in the inductor current, and that is when it constitutes a positive spike current. Now in this scenario second, when assume scenario 2, again the same point at point A, and Vs is going from negative to positive. So assume if S4 is on, now so before that it was turning on and it is not turned on. So during that time what we see is that there is a spike in the inductor current, or you can say that there is a positive spike in inductor current, sudden rise in the inductor current, because the voltage across this become suddenly very high across the inductor. Now when the S4 is on, whenever the S4 is on, the voltage across this will no longer be V naught, and that is when we have voltage across this inductor is very small, or you can say that nearly 0. So when S4 is on, so during that time there is no voltage across this, and you will see that there is voltage V naught with which the switch S3 capacitance get charged as S4 is already on. So what happens during that time, if S2 is on, that means for longer amount of time, for longer time duration, my VL is nearly equal to 0, or you can say that very small quantity, and that is when it has a very small positive slope. Now since S2 is closer to 1, that means now we are talking about we have now moved somewhere here. So after the S4 is on, we have moved sometime. So we have seen that, so S2 is on for longer duration, at the same time my S1 is on for a smaller duration, because it is because in a switching cycle if S2 is on for longer time duration, the S1 can be on for remaining duration only, which is very small. So during this instant when S1 is on for a smaller duration in a switching cycle, the voltage across the inductor is nothing but equal to Vs minus V naught. And since my Vs is closer to 0, what we will see is that VL will have, this VL is a very large negative value, very large negative quantity, and this, since we know that V is equals to L di dt, what we will see is that there is negative spike in inductor current. So what we have, when we are going from negative to positive, there is always a delay in S4 switch. Whenever there is a delay in S4 switch, we saw there is sudden rise in the inductor current in the positive side, and whenever the S4 switch is on, what we see is that there is a negative spike in the inductor current. So what we will see is that when it is going from negative to positive, there is a positive spike and negative spike, and whenever it is, and the same thing will happen in the case when it is going from positive to negative, when the input voltage is going from positive to negative direction. So what we see is that the inductor current, if it happens to be, what you want is, you want your inductor current to be average variation in switching cycle is going like this, and this actual current will be like this. If you know, if there is a large, if the switching frequency is larger than the, very much larger than the line frequency, then we have the inductor current. So this is your, or inductor current, or the input current looks like this. Average variation is sinusoidal, but it also have a ripple current. Instead of that, in case of totem pole PFC, what you will see is that this is the ideal case, ideal PFC case. What we will see in case of boost PFC, what we will see is that we have the average variation, we have this zero crossing distortion will be there, some positive spike and negative spike, and this will have this waveform will be like this shape, where this is nothing but, at these places if you see, it has nothing but called as a zero crossing distortion, and this zero crossing distortion will actually impacts TSD and power factor. That means if the power factor is unity, it will be measuring somewhere around 0.97, 0.98, 0.99, not exactly 1. And if you look very carefully, this zero crossing distortion we have discussed for going from negative to positive case. Similarly, there will also be there from positive to negative case as well. So this, every time whenever the grid voltage is going from positive to negative, we will see a zero crossing distortion. If we assume our grid voltage is like this, this is our Vs, and this will be our Is, and we have this zero crossing distortion where the current will be crossing 0 multiple times, because we have positive spike as well as negative spike, and that will keep on going for certain switching cycles. So that is why we will see the positive and negative spikes for some switching cycle near to 0 crossing of the line voltages, which is why this zero crossing distortion is one of the problems in case of totem pole PFC, especially if the output power requirement is very low. At light load condition, this distortion will be nearly equal to the peak value of the grid current. So that means this TSD and power factor will be very much impacted because of that. So that is why this zero crossing detection need to be addressed in case of totem pole PFC. There are soft turn on techniques which have been there in the literature, but which one can opt to take care this kind of zero crossing distortion. So in totem pole PFC, some of the advantages are, we have less number of devices, we have only 2 devices in conduction, we have one leg switching at a high switching frequency, another leg is switching at a low switching frequency, same as that of the line frequency, which is not, if you are having a 50 hertz AC, so 50 hertz with 50 hertz frequency. So you have reduced conduction loss, you have reduced switching loss, and at the same time reduce the component counts. So these are the advantage of totem pole PFC. However, it has a disadvantage, which is, having a zero crossing distortion in the current. Whenever the current is crossing the 0 from negative to positive or positive to negative, And also sometimes we require two kinds of switches, one for fast switching leg, one for slow switching leg. And this is the, I mean, these particular things have to be managed by the designer as well as manufacturer when they are using this converter as AC to DC converter of their EV charging system. Now in the next lecture we will discuss about discontinuous conduction mode of PFC converters. Thank you patiently for listening to this lecture.